In this video, we will show that the binomial distribution will tend to the Gaussian distribution as the number of experiments goes to infinity. First, let's revise the binomial distribution. When we have a series of experiments, let's say we have, for example, 4 experiments, the first experiment has some kind of probability of being successful, and the probability of being successful we will call P. And it also has some probability of being unsuccessful, and the probability of being unsuccessful is Q. Therefore, P plus Q is equal to 1. We just have 2 parameters to describe this kind of distribution here. And we also have the number of experiments, n. When we do experiments in a row, we have something like this. So for example, the first experiment has P probability of being successful, and the second one, for example, has Q probability of being unsuccessful. The third one has probability P of being successful, so I have P squared, and the last one has probability Q of being unsuccessful, so we have Q squared. So this kind of multiplication is related to the probability of having 2 successes and 2 failures. But I could also calculate the probability of having 3 successes and 1 failure, so P to the third, Q to the first power. And in general, I should also consider all the possible combinations of these failures and successes. So here, I should multiply this number by the binomial coefficient 4 choose 2, because I can arrange the events in whatever order I want. And this one, for example, would be 4 choose 3, or also 4 choose 1, because these are the same. I can either choose 1 failure or 3 successes out of the 4 experiments, and I will get the same number. In general, if I have k successes, I have p to the k, and therefore I will have n minus k failures. I will have to multiply this by n choose k, and this is my distribution. Why is it a distribution? Well, I have explained this with an example. Here you can understand from the example, but let's do it more rigorously. It is a distribution if I can sum all of this from k equal to 0 to infinity, and I have to prove that this is equal to 1 if it is actually a distribution, because the sum over all the possibilities should give me 100%, which is 1. So is this really equal to 1? Well, the answer is yes, because this is exactly the binomial coefficient, because mathematically this is related to the binomial theorem, P plus Q to the power n. And P plus Q to the power n can be exactly equated to this expression, but P plus Q is equal to 1. So 1 to the n gives me 1. And therefore, this is a distribution. You can also see it from here. In order to derive the theorem which relates the binomial distribution to the Gaussian distribution as the number of experiments goes to infinity, so n should be very large, we have to derive the average value or the mean value for the binomial distribution and also the variance of the binomial distribution. How do we calculate the average? The average is calculated like this: sum with k going from 0 to infinity of k times the distribution itself, so n over k, p to the k, q to the n minus k. I have to calculate this value. This is important because we will use it later. So how do we calculate it? We will calculate it from this equation here, where the distribution, when we sum overall values, we get the value 1. So we have to take the derivative on both sides of this equation, here and here, with respect to the variable p. If we take the derivative with respect to the variable p, on the left, I will get, so first I will have to take the derivative of this term, p to the k, but also remember that q is equal to 1 minus p, so I also have to take a chain rule there. So I have sum with k going from 0 to infinity, and then I have n choose k times k times p to the k minus 1 times q to the n minus k plus sum with the index k going from 0 to infinity n choose k times n minus k, p to the k, q to the n minus k minus 1. And I also have to take the derivative of q with respect to p, and this will be equal to the derivative of 1 with respect to p, because I also have to take the derivative of this term, but that's 0, so I get 0 here. And what is the derivative of q with respect to p? This is just minus 1, because q is equal to 1 minus p. And therefore, I can rewrite these expressions like this. This first one I can rewrite as 1 over p, which comes from this minus 1 here, times sum k from 0 to infinity. I have n choose k times k, p to the k, q to the n minus k, which is exactly what I want to derive. I want to derive a formula for this expression. And then I have minus from this one. And I have this first term, which multiplies the series that we have calculated at the beginning of this lecture. I have sum from k equal to 0 to infinity of n choose k times p to the k, q to the n minus k minus 1. But I can take 1 over q out of the summation, so I have n over q here, and then I have the sum, which gives me 1. So here I have n over q times 1. If you want, I have just n over q. And then I have minus. With another minus, I get a plus. Sum with k going from 0 to infinity, I can put out of the summation 1 over q. And then I have n choose k, k times p to the k times q to the n minus k. And this is equal to 0. And then I can put this to the right hand side, and I can sum this one with this one. So I have sum with k going from 0 to infinity, n choose k times k, p to the k, q to the n minus k. I can multiply this by 1 over p plus 1 over q, and this is equal to n over q. Now I can multiply both sides by the reciprocal of this. So I will get sum from k equal to 0 to infinity, n choose k times k, p to the k, q to the n minus k, and then I will have equal to n over q, and here I have 1 over p plus 1 over q. But now when I put these two together, I get n over q, and then I can rewrite this as p times q divided by p plus q. I can simplify this with this, and p plus q is just equal to 1. So the result here is n times p. This is the average of the variable k, which is distributed according to the binomial distribution. Now we also have to find the variance, and in order to find the variance, we have to do something very similar. We will have to calculate the derivative of both sides of this expression, because in this case we are interested in finding something similar. So I have sum from k equal to 0 to infinity, n choose k, but in this case I have k squared here, p to the k times q to the n minus k. So we have to find this, and in particular, first we will find this. This is not exactly the variance, because the variance, instead of k squared here, considers k minus the average, which is np squared. But in order to find the variance, we first have to calculate the average of k squared. So in order to find this, we have to consider the derivative of this expression on both sides with respect to p. So we are doing something very similar. Let me do it. So when I consider the derivative on both sides, I have 1 over p sum k from 0 to infinity. I have k squared, n choose k, p to the k, q to the n minus k. And this is just the derivative of this first term, because when I take the derivative of that, this k here will multiply this k, so I will get k squared here. And this 1 over p is simply due to the fact that when I take the derivative, here I have p to the k minus 1. So p to the minus 1 is 1 over p which I can put outside of the summation. But then I also have to take the derivative of this term, q to the n minus k, and similarly, I will get minus 1 over q. This minus sign is due to the fact that when I take the derivative of q with respect to p, I get a minus because of the chain rule. Sum with k going from 0 to infinity, k times n minus k, n choose k, and then I have p to the k, q to the n minus k, and this is equal to the derivative of np with respect to p, which is n. Now here I have to rewrite this second term. This second term contains a first part, k times n times the sum, which is something that we can do straight away because I can put this n outside of the summation, and then I have to sum over k times the binomial distribution, but I know what that sum is equal to. That sum is equal to n times p. So this part here will give me 1 over q times, I have n times p, and then I will have minus 1 over q sum over k from 0 to infinity. I get another minus from here, so I will get a plus k squared n choose k, p to the k, q to the n minus k. And now you get the idea, right? You get the idea because I simply have to solve for this summation, which is here and here. And I will skip the algebra in this case because this is very intuitive. If you understand how to do the first one, you can easily do this one yourself. And from here, we get the sum with k going from 0 to infinity of k squared n choose k, p to the k times q to the n minus k. You will get that this is equal to n times p times q plus np squared, just like this. It's just algebra. And now from this result, you can also get the variance. So the variance is calculated like this, sum from k equal to 0 to infinity, k minus np squared, n choose k, p to the k, q to the n minus k. Now here you can simply square these parentheses, you get k squared plus np squared minus 2np times k. And you get three terms, and you can calculate the three terms, because when you get k squared, for example, you can refer to this formula here, and then you have np squared, which you can put outside of the summation, so you will get just 1 in that case. So you will get the first term, k squared, is just equal to this 1, so you get npq plus np squared, and then the second term is equal to np squared times 1, because you simply have the summation of the binomial distribution from 0 to infinity, which will give you 1. And finally, you have minus 2np times the summation over k, in that case, times the binomial distribution n choose k, p to the k, q to the n minus k. But that one gives you n times p. So you will get some terms that cancel, and you are left with npq. So I can cancel these terms here, and the result for the variance is this one. In order to show that the binomial distribution goes to the Gaussian distribution as n goes to infinity or n grows larger, we had to know the variance and the average of the binomial distribution. These values here, these results are important. NPQ and NP are the results that we will use. And now we can finally do the derivation for the binomial distribution tending to the Gaussian one. We have to consider n choose k, p to the k, q to the n minus k, and now we will do some mathematical steps to show that as n grows larger, this will go to the Gaussian distribution. So the binomial coefficient can be written as n factorial divided by n minus k factorial, k factorial here, and then I have p to the k times q to the n minus k. Now, this is the point at which we will use the Stirling approximation. I have shown how to derive the Stirling approximation mathematically in a previous video, so you can check the derivation if you don't remember how to derive it, or if you just want to know the formula, I will give the formula here. This is approximately equal to when n is reasonably large, but n does not have to be very, very large for the Stirling approximation to be acceptable. N factorial can be written as n to the power n, e to the minus n, and then I have the square root of 2 pi n. And something similar for n minus k factorial. So when I divide, here I have n minus k raised to the power n minus k, e to the minus n minus k, and then I have square root of 2 pi n minus k, and then I have k factorial, which is k to the k, e to the minus k, square root of 2 pi k, and then this multiplies p to the k, q to the n minus k. Now let's rewrite this more concisely. This is equal to, I have n times p over k raised to the power k, and then I have n times q divided by n minus k to the power n minus k. So you can check that these terms here are equal to this one together with this one together with this one here. You can check that they are exactly the same. Then you can also check that e to the minus n, e to the minus n minus k, and e to the minus k will cancel. It's easy to see. And then I will be left with the square root of n divided by 2 pi k times n minus k here in the denominator. And now here we will do another approximation. The approximation is that k will be very close to its average, np, and this approximation will be better as n increases, because if the number of trials, if the number of experiments increases, k will become closer and closer to its average, which is np. Remember, we derived the average np earlier. So here I get the square root of 1 over 2 pi n times p times q. You also have to remember that p is equal to 1 minus q, and I have simply rewritten the content of this square root. Then I have n times p over k to the k, n times q divided by n minus k to the power n minus k. Now we will rewrite these terms here. We will consider the exponential of the logarithm. So I will rewrite these terms as the exponential of the natural logarithm of those terms. np over k to the k, nq divided by n minus k to the n minus k. And for the properties of the logarithm, we can rewrite that as exp of k times the logarithm of np over k, or if you want, minus k times the logarithm of k over np. And then I have plus k minus n times the logarithm of n minus k over nq. This is just for the properties of logarithms and exponentials. So the exponential of the logarithm is simply equal to the argument of the logarithm. This is just a simple mathematical trick which will help us in the derivation. And now we will consider a substitution. So I will define the variable x, which is another random variable, and it will be equal to the variable k minus np divided by the square root of npq. So I have simply subtracted the average from the variable k and also divided by the square root of the variance, or if you want, the square root of the variance is the standard deviation. This means that x will be distributed according to the binomial distribution, but the average of the variable x is 0 because I have subtracted np from k. So when I take the average of x, I will get 0 because I have k minus np. The average of k minus np will be 0 because the average of k is np, and np is just a scalar, so I have np minus np. And also the standard deviation of x will be equal to 1 because when I take the variance of this variable, I will get npq in the numerator and also npq in the denominator because we have to square this, so I will get 1. This will just simplify our derivation if I consider this variable x. This variable x plays the same role as the variable k, but it will have a 0 mean and the variance is equal to 1. So if I substitute in here, and what do I have to substitute? Actually, I can rewrite this as k equal to x times square root of npq plus np. I will substitute for k this quantity. So let me rewrite this expression. Here, this is equal to 1 over the square root of 2 pi npq exponential of minus k, and here I have logarithm of, when I substitute this expression inside this logarithm, I will get 1 plus x times square root of npq divided by np. And then I have plus k minus n logarithm of, I do the same in here, I have 1 minus x times the square root of npq divided by nq. And now I'm going to consider a Taylor series of these logarithms, this one and this one, which I will truncate to the second order. Why can I consider a Taylor series? Well, because here I have square root of n over n, which is 1 over square root of n. So it means that since n is going to be very large, this quantity here will be quite small, right? Because I have square root n in the denominator, because square root of n over n is 1 over square root of n. So the denominator will dominate the numerator. So the argument here would be 1 plus a small quantity, so it is almost equal to 1. And the logarithm of something which is close to 1, it is close to 0. And remember the approximation for logarithm of 1 plus x, so the Taylor series will be x minus x squared over 2 plus x cubed over 3 plus dot dot dot. So you can derive the Taylor series for the logarithm of 1 plus x as x goes to 0. And we will not consider terms which are of higher order with respect to the second order. So we will consider only the first two terms because we are interested only in the second order. So let's do this computation. This is approximately equal to 1 over square root of 2 pi n pq. And then I have the exponential of, I have minus k, and this multiplies x times square root of q over np minus x squared q over 2np plus higher order terms, which I'm not interested in. Then I have plus k minus n minus x square root of p over nq minus x squared p divided by 2nq plus higher order terms. Let me close the curly brackets, and this is equal to 1 over square root of 2 pi n pq exponential of, now instead of minus k, I can rewrite k by using this formula here. So I have minus np minus x times the square root of npq, which multiplies x times the square root of q over np minus x squared q over 2np plus I order terms plus k minus n. So in this case, I rewrite k as np plus x square root of npq minus n times minus x square root of p over nq minus x squared p over 2nq plus dot dot dot. This is approximately equal to 1 over square root of 2 pi n pq exponential of. Now I'm going to multiply out these terms with these terms. First I multiply this with this, so I get minus x times the square root of npq, and then I multiply this with this, and I get plus x squared q over 2, and then I multiply this with this, which will give me minus x squared q, and then I should in principle multiply this with this, but I multiply square root of npq with the 1 over np here, and I get 1 over square root of n. So this is a term of higher order, so I can neglect this. I will get plus dot 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 plus, and then here I will have to multiply this with this, but first let me put together np minus n. np minus n is n times p minus 1, so that's minus nq. When I multiply minus nq with minus x square root of p over nq, I will get plus x times the square root of npq, and then I will get plus x squared p over 2, which comes from the multiplication between minus nq and this second term here, and then I get minus x squared p, which comes from the multiplication between this one and this one, and I have higher order terms. Now you can see that this term, which is the largest inside this exponential, will cancel this one. It is the largest because it multiplies square root of n, but that will cancel. And if I do the algebra here, we get 1 over square root of 2 pi n pq exponential of, now I get these terms here sum together. So from the first one here I get minus x squared q over 2, and these two together will give me minus x squared p over 2. And if I put these two together, I get minus x squared over 2 times p plus q. But p plus q is equal to 1, as we know. So this gives me 1 over square root of 2 pi n pq. And then I have the exponential. Now I can rewrite it like this, e to the minus x squared over 2. But I will rewrite the expression for x that we wrote here. If I square that, I get minus k minus np squared over 2 npq. And lo and behold, we have found exactly the Gaussian distribution of the variable k, and you can see that the average of the distribution is here, and we also get the variance of the distribution here in the denominator. So we have found that the binomial distribution with average np and with variance npq will become a Gaussian distribution with average np and variance npq as n grows larger and larger.